Hi, we meet again. Okay, for this part 3 of lecture 15, we're going to proceed with examples related to the Biot Savart law based on formulations that we have developed so far. Okay, so in this example number 1, we are given a line current, yeah, given in a form of AB line, having a amplitude, the magnitude of the current is 6 ampere. So the location, the starting point of this current is at point B and at the point of A. Yeah, so the coordinate for B is 1, 0, and the coordinate of A is 0, 1. So this is a two-dimensional problem. Okay, we can just have X and Y axis. Right. So based on this given problem, we can see that this is a finite length of filament current. Okay, and based on what we have learned so far, the H field for due to the AB current can be written as I over 4 pi of R, okay, sine of alpha 1 plus sine of alpha 2, the direction of phi. Okay, this is based on formulation that we have developed in part 2 of lecture 15. Yeah, you can recall back, you can refer back to part 2 of lecture 15 on this H field intensity for the case of finite length of filament current. Okay, and then there are three things need to be obtained. The first one is the R, which is a distance, a perpendicular distance from the filament current to the point of the origin, which is the point of interest. And then you have to find out y sine of alpha 1 and y sine of alpha 2. Okay, so let us do it one by one. Regarding the R, so R should be a distance perpendicular from the filament to the point of interest. So that should be your R. Okay, and doing this, you can see that the distance here, okay, the distance of AB. So AB shall be equals to set of 2 by using a Pythagoras theorem. Okay, and then based on that, if I put that this point here is a point of X, so I can see that AX distance shall be equals to set 2 divided by 2. Yeah, we use AB divided by 2 lah. So that should be the distance of AX. Okay, and from this onwards, we can see that the R, which is the perpendicular distance, shall be equals to set of 1, which is the hypotenuse, 1 squared, minus the AX or the BX squared, which is set 2 divided by 2 squared. Okay, so that should be our AX, sorry, it's BX, yeah, BX. Yeah, and then we're going to have it as set of 1 minus 2 divided by 4 or half, so we're going to have set of half. So that should be the perpendicular distance from the filament current to the point of interest, which is the origin. Okay, whereas for the sine of alpha 1, so we just take that this alpha 1 is here and alpha 2 is here. So from here we can see that the sine of alpha 1 shall be equals to the bx, yeah, the bx over the hypotenuse, which is 1. And we can just have it as equals to set 2 divided by 2. And similarly for sine of alpha 2, we're going to have it as ax over 1, and that will give us set 2 of alpha 2 also. And from these three informations obtained, we can then get that the H field due to this AB filament current or line current having 6 ampere magnitude should be calculated as 6 divided by 4 pi of R. So R is set of half. Okay, and then we have sine of alpha 1, which is set of 2 divided by 2 plus sine of alpha 2, which is also set 2 divided by 2, and then we have the direction of phi. Okay, and we can simplify it to be equals to 6 divided by 4 pi, okay, set of 1 over 2, and then we have these should be equals to set of 2. Okay, and then we have the direction of phi in ampere per meter. Okay, but care has to be taken because remember, this particular equations is obtained, yeah, these equations that we use here is obtained when we consider that your line current is located on the z-axis. Yeah, so when your line current is located on the z-axis, yeah, if you refer back to lecture part 2 of this lecture, the equation of H here is obtained when the line current is located on the z-axis, so the H field will be in the phi direction. Yeah, so but in this particular case, your line current is not located on the z-axis, yeah, but somehow it is located between the x and y plane, yeah. So you have to rework on what should be the direction of the phi now, yeah. And this direction of phi basically is obtained from understanding that the equation of Biot Savart state that H field equals to integration of I dl cross r divided by 4 pi r power of 3, in which the direction of phi is obtained from the cross product between the current direction and also the r, which is the vector from the filament to the point of interest. Yeah, that r vector is a vector from the filament current to the point of interest, and then we get the direction of phi. So we can say that in general, we can write that the direction of phi here is basically based on the unit vector of current direction, which is, I just put L here, cross product with the direction of R, which is the direction of distance from the filament current to the point of interest. So in general, we can represent that the phi direction shall be or can be obtained by using the cross product of these L cross R. Okay, so we're now going to apply this information to this phi direction of the H. So I can write that the phi basically is written as direction of current cross direction of R. So you have to obtain what should be the direction of current based on this diagram and what should be the direction of R from this diagram. Okay, so if we base on this, we know that the direction of current is given by this L. Okay, so I can write here that the L shall be equals to the vector, yeah, the vector from B to A, in which we know that the point here is 0, 1, and the point here is 1, 0. So in the vector of L can be written as negative of x plus direction of y. Okay, this point minus this point, yeah. 0 minus 1 will be negative x, 1 minus 0 will be positive y, and divided by the distance between A and B, which is set of 2. So that will give us the unit vector of the L. Whereas for unit vector of R, basically unit vector of R is this unit vector from which is based on the perpendicular distance, yeah, perpendicular distance or radial distance, yeah, from the filament to the point of interest here. So that should be your unit vector of R, yeah, and we know that the point here, this coordinate should be equals to half and half, yeah, because located at the center, yeah, and from here we can set in the vector of R will be equals to negative half of x minus half of y divided by the distance, in which we have obtained distance before, which is equals to R is equals to third of half, yeah, third of half. Okay, so that should be our unit vector of the R. Okay, so we're going to do the cross product now, in which the phi shall be based on this cross product where we have negative of x plus y divided by third of 2. Okay, cross product with the negative half of x, yeah, minus half of y divided by third of half. Okay, so that should be the cross product between the L and the R. Okay, and if you work for this cross product, yeah, basically this can be cancelled out. Okay, and if you work for this cross product, basically you're going to get something on the z-axis. Yeah, the resultant direction for the H field will be on the z-axis. Or sorry, z direction. I apologize. Yeah, direction of the H field should be in the z direction. So please work out for this. Yeah, for instance, yeah, if I say that, yeah, x cross x will give us 0, but x cross y will give us z. Yeah, x cross y will give us z. So you can work for this cross product between L and R and end up going to get that the direction of the H field finally will give us the direction of Z. Yeah. Okay, so I left this for you to prove it on your own. Yeah, that the H field will be on the Z direction. Okay, so I hope that's clear on the calculation of the H field based on the line current problem. Yeah. Okay, let's have a look at example number 2. So for example number 2, we are given a case of square conducting loop of side 2A, which lies in the z equal to 0 plane, and carries a current of I in the counterclockwise direction. Okay, and the question is to find the magnetic field intensity at the center of the loop. Okay, so we are having this particular case. Okay, right, this is the z-axis, sorry. There, so that should be our x-axis and that should be our y-axis. Okay, so the okay, so the um, square conducting loop should be given by these black lines. Okay, so we are having the distance is 2a, yeah, so which means that this is 2a, all right, this is 2a and that's also 2a, yeah, it's a square. So the question is to find, okay, before that, the current I is in the counterclockwise direction, so that should be our I, counterclockwise direction, right, and you need to find the H field at the center here, at this particular point. Let's say we put the point is at 0, yeah, or the O point is the center of the loop. Okay, so we know that this particular square is composed of 4 sides. Yeah? Let's say we have, we label this as side number 1 should be here, side number 2 should be there, side number 3 should be there, and side number 4 should be here. Okay, so we need to find the H field contributed by each side one by one. Let's say we start with side number 1 first. Okay, side number 1, let's say we have side number 1 is here, that's the origin. Okay, and we want to find what should be the contribution of the H field, sorry, contribution of the I for side number 1, this side, to the point of interest, which is at the origin. Okay, so we know that the distance is A, yeah, so that's the distance, which is a perpendicular distance, which should be A, yeah, and the distance here is 2A. Okay, and basically from here we know that the H field contributed by this filament of length of 2A shall be given by H, should be I over 2 pi, sorry, 4 pi R, yeah, 4 pi R, sine of alpha 1 plus sine of alpha 2, direction of phi. Okay, so we have the I, just give the symbol of I only, there's no value for the I, so we have I, 4 pi of A, so R is A because A is a perpendicular distance, yeah, radial distance from the filament to the point of interest. Okay, sine of alpha 1, okay, we can use sine alpha 1 should be there, okay, so that should be our alpha 1, and that should be our alpha 2. Okay, so sine alpha 1 will be A divided by set of, okay, so this particular case is set of A squared plus A squared, okay, and we're going to get this as set of 2 of A, yeah, so that should be our sine of, sorry, the hypotenuse length, yeah, so that will give us the sine of alpha 1 should be equals to A divided by set 2 of A, and similarly for sine of alpha 2 we're going to get about the same form, which is A divided by set 2 of A, yeah, and direction of phi. So this A can be cancelled out. Okay, so we're going to get this as I, okay, I over 2 pi A square root of 2 and direction of phi. Okay, and because your filament current is not located on the z-axis, yeah, because it's located here, which is not on the z-axis, so we need to change the phi to be direction of current cross direction of R. So based on this diagram, we know that the L should be in this direction, which is equals to direction of y positive, yeah, whereas for the direction for the unit vector of R, which is in this direction from the filament to the point of interest, that's the direction of R, and if based on this, the direction should be in the negative x, yeah, R should be in the negative x direction. So based on this, we have the phi to be direction of L cross direction of R, and that will give us y cross negative x direction. Okay, so what should be the direction for y cross negative x? What should be the result for the cross product? So we know that from this cross product, the direction will be in the z direction. Yeah. Okay, so we can write that the H field will be I divided by 2 pi A square root of 2 in the direction of positive z. Okay, so you can prove this is what we obtained for the first side of the square loop. Yeah, you can prove on your own that for side 2, 3, and 4, you're going to get the same form of H field. So due to that, you can see that the total H field produced by this square conducting loop to the point of interest, which is at the origin, shall be equals to 4 multiplied with this H field obtained, which is 4i of 2 pi a square root of 2 in the direction of z in ampere per meter. So that should be the H field in total. Yeah. Okay, hopefully you are clear about this example. Okay, so we proceed with the example number 3, in which you are having an infinite long semiconductor, which is now bent into an L shape as shown in the figure below. The current is 5 ampere flowing in the conductor, and need to find the magnetic intensity at the point of 2 to 0, yeah, 2 to 0. Okay, so basically this particular line is infinite, yeah, it's infinite, which is starting from like infinite at the x-axis, and it goes straight away to the infinite along the y-axis. Okay, and we need to find H field intensity at the point of 2 to 0, sorry. So 2 to 0 somehow located here, okay, which is, this is 2 to 0, that should be the point of interest, okay. And if you base on this example, although it mentioned here that the conductor is infinite, but we need to separate this particular infinitely long conductor into two different regions. The first one is on the x-axis, and the second one is on the z-axis, because it's not a straight line anymore. Yeah. If you want to use the equation that has been simplified, remember we have H field equals to I over 2 pi r direction of phi. Okay, this equation is obtained from the argument that the finite length of line current has been extended, has been increased in terms of its length, in which it produced the infinitely long line current, and we have simplified the equation to be just I over 2 pi r direction of phi. So this equation is valid only if the line current is straight in nature from negative infinite to positive infinite. But for this particular case, since the line has been bent, it has been bent, so we cannot use these equations, yeah, it's not valid anymore. Instead, we need to separate into two sections, so we can consider that each section here is a case of finite length of line current, yeah, finite length of line current. Okay, so for this, let's say we consider line current number 1, yeah, so we can see that the H field will be calculated as I over 4 pi r sine of alpha 1 plus sine of alpha 2 direction of phi. You have to use this equation again, yeah, because we are dealing with the finite length of filament current. So we have I, which is 5 ampere divided by 4 pi of r. R is a radial distance or perpendicular distance from the filament to the point of interest. So we know that from this diagram, yeah, from this diagram, we know that the R is given by this length. That should be the R, yeah? And we know that the coordinate of this is 2 to 0, so R shall be equals to 2. Yeah, so we have 2 for the R value. And for the sine of alpha 1, so we need to know exactly where's the alpha 1 and where's the alpha 2. So I can see that alpha 1 is the angle made between, yeah, we know that alpha 1 and alpha 2, both of them are the angle made between the end of the filament current to the point of interest. So the end of the filament is here, one of it is here, and the one is located at infinite. So that should be the angle, yeah? So let's say we take this as alpha 1, and that should be the alpha 2. Okay, so from here we can say that sine of alpha 1 will be this length, yeah, will be this length, that should be the length, which is 2, divided by this hypotenuse. And we know that this is 2 and this is 2, so the hypotenuse should be equals to set of 2 squared plus 2 squared, so that should give us set of 8, yeah, set of 8. And so for that, we can see the sine of alpha 1 will be equals to 2 divided by set of 8. Yeah. Whereas if we base on this diagram, alpha 2 will be approaching 90 degrees. So sine 90 will be equals to 1. Yeah, so we can just put sine alpha 2 should be equals to 1, because if based on this, alpha 2 is said to be approaching 90 degrees because the endpoint is located at infinite. Yeah. Okay, so that should be the phi direction. And then we're going to proceed with the solution. So that will give us 5 over 8 pi. And for this, you can work out for the value, yeah, 1 plus 2 over third of 8. Right, and for the phi direction, we need to change it into the L cross R. Because why? Because your current is not in the Z direction, so we need to change it into L cross R. So we know that from here, the phi will be L cross the R. So L is in the negative x, sorry, yeah, because the current is in this direction. So L should be negative x, whereas the R, if you base on this, R is towards this direction, which is in a y direction. So x cross negative x cross y. So negative x cross y will give us negative z direction, yeah? Negative z direction for the phi, yeah? Right, so that should be the H field due to site number 1 or the filament number 1, yeah, which is extended from infinite to 0 along the x-axis. Okay, so we can now proceed with the H2, which is produced by the filament number 2, yeah, filament number 2, this filament on the y-axis. Okay, so we can see that for filament number 2, you're going to get that the H field shall be equals to, again, I over 4 pi of R, a sine of alpha 1 plus sine of alpha 2 direction of phi. Okay, so I is 5 ampere, 4 pi. So R, if you base on this diagram, so that should be the, yeah, that should be our perpendicular distance. Right, and we know that the coordinate is 2 to 0. So again, you're going to get R equals to 2. Okay, and sine alpha 1, I think the idea should be the same as before. Yeah, in which you're going to get this sine of alpha 1 to be 2 over third of 8. Yeah, 2 over third of 8, sorry, 2 over third of 8. Whereas sine alpha 2 will also give us 1, yeah? Because if we can label the angle, alpha 1 is here and alpha 2 is here. So alpha 2 will be approaching 90 degrees. Yeah, so that sine 90 degrees will give us 1, whereas for sine of alpha 1, based on this position of the angle alpha 1, we're going to get it should be 2 over the hypotenuse, which is third of 8. Yeah, and then we have the unit vector of phi. Right, so almost similar with the answer here. So we're going to get 5 over 8 pi, and please solve for this inner value, 2 over third of 8. Whereas for this unit vector of phi, which is L cross R. Okay, so in the vector of phi, based on this diagram here, L is in the y direction, whereas R, if you base on this diagram, R is towards this point, yeah, which is R must always directed from the filament current to the point of interest. So based on this, the direction of R is positive x, yeah? So y cross x will give us negative z direction. So that's what we're going to have in the vector of phi to be negative z direction. Yeah, so basically the terms for H field for site number 2 is similar to the terms of H field due to site number 1. So to find the H field at 220, we just add them together. Yeah, we just add them together. So that would be the total H field produced by this filament current of infinite length, but not in a straight line. Yeah, it has been bent at the origin. Okay, for part B, which is point of 002, so I left this for you to solve this on your own, yeah, because the idea is similar. We just change the location, the point of interest, yeah, to the point of 002. Yeah, if you have any questions on this method of solution for part B, you can always consult me using the Telegram, yeah. Okay, let us proceed with example number 4. This example, we are given two axes located on the y and the z axis respectively, which carries a filament current of 10 ampere along y and 20 ampere along negative z. The question is find the H field at the point of negative 3, 4, and 5. Okay then. Let us sketch the diagram for these problems. Okay, this is your z-axis, that is your x-axis, and that should be your y-axis. Okay, all right. So we have the 10 ampere along the y. Yeah, so if we can label it as a, yeah, if we can label this as a line, yeah, right. There's a line here, right? So that should be 10 ampere in the y direction. Okay, this is 10 ampere. Then we have 20 ampere along negative z. Yeah, so we have another 10 ampere on the negative z. So we have this current directed downward. This is 20 ampere, negative z direction. So the question is to find the H field at the point of negative 3, 4, and 5. So where's the location of negative 3, 4, and 5? So negative 3 should be here. Okay, so 4 should be here, and 5 should be here. So location of the point somehow should be located here. Okay, so that should be negative 3, 4, and 5. Okay, so we need to find the H field at this position, yeah? And in this particular case, we are given two filament current of 10 ampere along Y and 20 ampere along negative Z. But we are not given any information about the length of this filament current. So what we can do is that we can assume that the length is infinite. So since the length is infinite, we can use the equation that we have learned before, where H field which should be equals to I over 2 pi r direction of phi. Okay, and since we have two filament current, we just label that the first one is here on the y-axis, and second one is here on the z-axis. Okay, so for the first filament current on the y-axis, you can see that the H field due to filament current number 1 should be equals to I, which is 10 ampere, divided by 2 pi of r. So r is a perpendicular distance from the filament of 10 ampere to the point of negative 3, 4, and 5. Yeah, so if we base on this, we shall know that the perpendicular distance should be given by this, yeah, should be given by this line. Okay, let me use the color or the blue color. Okay, should be given by this line then, yeah, if we can plot it. Okay, so that should be the line that will give us the perpendicular distance. Yeah, so that should be the distance. Okay, in which the point on the y-axis that will give a perpendicular distance with the point of negative 3, 4, and 5 should be the point of 0, 4, 0. Yeah, that should be the point that will make a perpendicular distance with the point of negative 3, 4, and 5. So based on that, we can see that the distance between the point of 0, 4, 0 and negative 3, 4, and 5 shall be given by set of 3 squared plus 5 squared, which will give us set of 34. Yeah, set of 34. So we get that the R should be equal to set of 34. Yeah, and then we have the phi angle, phi unit vector, phi unit vector. And the phi unit vector, we need to change it into the L cross R. Okay, L cross R. And further on, we can proceed. We can have 10 over 2 pi set of 34. The L should be in the y direction, yeah, because the current is in the y direction. But the R is directed from the filament to this point. So that should be the R direction. Yeah, that should be the R direction from this 0, 4, 0 to the point of negative 3, 4, and 5. So based on that, we can see that the R in the vector for this particular case should be equals to negative 3 of x plus 5 of z. Yeah, because negative 3, 4, 5 should be the end point, and 0, 4, 0 should be the starting point. So the vector for that will be negative 3 of x plus 5 of z. But in terms of the vector, that should be divided by the distance, which is set of 34. Okay, so that we're going to have the unit vector of r to be negative 3 of x plus 5 direction of z divided by set of 34. So we can rework for this. We can have the H field shall be equal to set of 10 over 2 times 34, which will give us 68 pi Yeah, because 34 set and 34 set will be 34. Yeah, 34 times 2 will be 68 pi. And y cross negative x will give us 3 of z. Okay, 3 of z. And then y cross z will give us 5 of x. Okay, so that should be the H field that is produced by the the filament current number 1. Okay, we have the H field due to filament number 1 will be 10 over 68 pi in the direction of 3z plus 5 of x. Yeah? Okay, so that should be the H field due to first filament current. So let us proceed with the second filament current. Let me erase all of this. Okay. Right, so for this filament, for the second filament, which is at 20 ampere along Z, let me resketch it again. Okay, this is X, this is Y, that should be Z. Okay, so the point of your interest, the point of interest is at negative 3, 4, and 5. Negative 3 should be there. Sorry, negative should be there. I apologize, should be there. This is 4. That should be 4, and that should be 5. Okay, so that should be the point of interest. Okay, that should be negative 3, 4, and 5 coordinate. Your line current is located here. It's located here. That should be the line current, but in the negative z direction. That should be 20 ampere. Okay, so again, by using equation, this is for filament number 2. Yeah, H field will be equals to I, which is 20 ampere over 2 pi of R. R is a distance from the filament to this negative 3, 4, and 5. R is a radial distance. Yeah, I'm using H equals to I over 2 pi R direction of phi. Yeah, I'm using this equation here. So R is a radial distance. So based on this, we know that radial distance is this distance. Yeah, we given by a distance between negative 3, 4, and 5 and the point of 0, 0, 5. Yeah, so that will give us a perpendicular distance, and based on this, we can say the distance will be equals to set of 3 squared plus 4 squared, and then we're going to get this as equals to 5. Huh? Yeah, so 5 is a distance perpendicular from the filament current to the point of negative 3, 4, and 5. Yeah, so that should give us 5 as the distance. And for the phi, need to change it into the L cross R, so that will give us L cross the R. So the L is directed downward, so that should give us negative Z direction. Whereas for the R, which is direct unit vector from 0, 0, 5 to 3, negative 3, 4, and 5. So unit vector of R here should be equals to negative 3 of X plus 4 of Y divided by 5. So then we're going to get the R unit vector to be negative 3 of X plus 4 of Y divided by 5. And the L cross R results for this will give us 3 over 5 Y. Okay, and for Z, negative Z cross 4Y, so that will give us, so Z cross Y will give us negative X, and negative is positive. So that will give us plus 4x direction over 5. Yeah, so that should be the representation for the phi. So substitute this into the phi, so we're going to get the H field due to the second filament current to be 20, yeah, over 50 pi, yeah, 50 pi, and in the vector for this will be 3 direction of y plus 4 direction of x in the ampere per meter unit. Yeah, so that should be our H field produced by filament number 2. So the total H field produced by both filament current is just summation of these values. Yeah, right. Hopefully you understand about the solution for example 4. Yeah. Okay, so let's have a look at example number 5, which is to find the expression for the H field along the axis of the circular current loop having a radius of A and carrying a current of I. Okay, so if we can resketch this diagram, so it should look like this. Yeah, we're having now a circular current loop. Yeah, having a radius of A. yeah, radius of A, and it carries a current of I, so we just put that I is here. So need to find the H field along the axis. So the axis is considered to be the axis here. Okay, we put this should be on the Z axis. So we need to find what should be the H field produced by this filament current in a circular loop structure to the point on the Z axis, any point on the Z axis having a coordinate of 0, 0, Z, for instance. So we need to find the H field at this position of 0, 0, Z. Okay, so for this, we need to go back to the basic of Biot Savart's law because this is not a straight line. Eh? So since it's not a straight line, we cannot use the equation that has the sign of alpha 1 and sign of alpha 2 that we have formulated before. Yeah? So we have to go back to the basic of Biot Savart's law. Remember the 3 steps that we have mentioned to you before. Yeah, 3 steps. Yeah, we have step number 1 is to identify the current element. So in this particular case, your element is here. Yeah, this is the element of current. This is a DL vector. Yeah, so we can put that the element of the current is I DL vector, and this is can be written as I of R d phi, direction of phi. Yeah, so that should be our element of current for this problem. Yeah. Okay, and for step number 2 is to find the DH produced by this DL element. So the DH, yeah, is produced by this DL element. So if we can, based on this, your DH is produced by this element. Sorry, it's my mistake. Sorry for this. Yeah, I need to resketch it again for you. Not nice. Yeah, my drawing is not nice. Sorry for that. Okay, right. Need to resketch again. Sorry for that. Okay. So we have that should be the filament. Okay, that should be the axis. Okay, and this is the point of 0, 0, Z. The current is in this direction. Here is I, and the element is here. Yeah, sorry, this is the element of the L vector over there. Yeah, that's with the DL vector element. So the DH is produced by this DL element to this point of 0, 0, Z. So that should be the DH. Yeah, the DH. Okay, so we can say that the DH based on the Biot Savart's law will be I dl vector cross R divided by 4 pi R power of 3. Okay, so we just substitute the respective dl vector. So we have I of R d phi, direction of phi, cross product with the vector of R. Okay, the vector of R is a vector directed from the dl element to the point of 0, 0, Z. Yeah, so that should be your vector of R. So the vector of R is given by this vector plus this vector. Yeah, so knowing that the loop is having a radius of A, so I can write that the vector of R shall be equals to A, direction of negative R, plus this height, which is Z, direction of Z. So that will give us A squared plus Z squared. Sorry, this is not the magnitude, it's a vector. Yeah, so that will give us A, direction of negative R, plus Z, direction of Z. And following this, we can find the magnitude, which will give us A squared plus Z squared power of half. Okay, so we substitute all of this information into the equations here. So we're going to get A, direction of negative R, plus Z, direction of Z, divided by A squared, sorry, 4 pi should be there, A squared plus Z squared power to 3 over 2. Yeah, so that should be our DH, yeah, our DH. And for the third step is to find the H field. So allow me to erase this part then. Yeah. Okay. So that's your DL just now. Okay. So for the third step is to find the H field. So H field will be in this integration of DH. Okay, and that we're going to have this as integrations of these terms that we're going to have I R, before that, allow me to do the cross product first. Yeah, we need to do the cross product first. Sorry for this, my mistake. We need to do the cross product first before we proceed with the H field. Okay, so we're going to have it as I R d phi, okay, over 4 pi a squared plus z squared to the power of 3 over 2. Okay, so this cross product will give us a phi cross negative r, yeah. So phi cross negative r basically will give us negative z, yeah. Phi cross r will be negative z, but since we have negative sign there, so we have z direction, yeah. And for the phi cross z, yeah, so that will give us r direction, yeah. So we're going to have plus the z direction of r, okay. So that should be the dh vectors, yeah. So we're going to have that the dh vectors consists of the z direction and also the r direction. Okay, so the next step, step number 3, is to find the h field. So h field will be the integration of the dh. Okay, so we need to integrate these terms of dh here. So the integrations of I r d phi divided by 4 pi a squared plus z squared power to 3 over 2, yeah, is direction of z plus z direction of r. Okay, so if you based on this integration, yeah, so we are integrating towards the d phi, which is in the closed closed loop, means that we are integrating towards the overall circle, yeah, overall circles, which in which the integration of phi will be from 0 to 2 pi, yeah. So this idea is similar to what we have done before for the case of calculating the line charge, for the case of circular charge structure, remember? Yeah, where we need to consider the case of symmetrical issues, yeah, in which if we have a DL here, we're going to have also a DL over here, in which if we base on this in a vector, we can see that the effect of the R will be cancelled out. Yeah, the effect of R will be cancelled out, and we left only with the contribution from the Z direction of H field. Yeah, so R will cancel out due to the symmetrical contribution, yeah, of the same DL at the opposite side. Yeah. Okay, but this idea is valid only if your I here, your current is uniform, then this idea is valid. Yeah, if I is not uniform, so this cancellation idea is not valid. Yeah. Okay, so since this R has been cancelled out due to the symmetrical effect, so we can straight away do the integration. So we're going to have I RA, and then we have 2 pi then divided by 4 pi of A squared plus Z squared power to 3 over 2, and then can be simplified. We're going to have, sorry, the direction of the angle is Z just now, yeah? Z direction. So we have this as I RA, direction of Z, divided by 2 of A squared plus Z squared power to 3 over 2. Okay, so that should be our H field intensity. Do I make any mistakes here then? Okay, sorry, I make a mistake. Sorry for that. It's my mistakes. Yeah. We are supposed to get, yeah, this is not R. Yeah? This is A supposedly. Yeah. That should be A. Okay. This is also A. This is also A, and that should be also A. Yeah. So it means that we are having A squared lah. Yeah. A squared. If you have A here, this is A d phi. Yeah. This is ADV. Supposedly it's ADV, not R, yeah? Because the DL is calculated on the curve of your circular structure. So the DL should be ADV, not RDV, yeah? Okay, so that's why we're going to have this to be A squared. Yeah, A squared. I can just take out the, yeah, that should be the A squared. Okay, for that should be cancelled out. There should be no Z. There should be no Z also. So we only have A squared and also A squared here. Yeah, and it should give us A squared. Yeah, so that should be the answer for your H field, in which A is the radius of your circular loop, Z is the variable, so in which the H field that we have calculated here is the H field at any point on the Z axis having a coordinate of 0, 0, Z. So the unit will be in ampere per meter. Okay then, yeah. So hopefully you are clear regarding, understand clearly on this example, yeah, on calculation of H field due to a circular loop current. Okay, right. For example 6, okay, example 6 is about solenoid. Solenoid. I hope you understand, you know what solenoid is all about. Solenoid is a current that is in form of circular loop. Yeah, we have structure like this. Okay, sorry for that. We have the cylindrical structure, and the current is flowing in this particular cylindrical manner. Yeah, so some sort like a windings, yeah? Windings on a circular, on a cylindrical structure. So we call this a solenoid. Yeah, somehow we can see this in dynamo. Yeah, we have a solenoid. Yeah, so the solenoid in this particular case is having a length of L. Yeah, the length is L, and it consists of the N windings, N turns. So we have N turns of the solenoid, and each this these windings carries a current of I. Yeah, I current which is exists in this N turns of wire. So we need to find the magnetic field intensity at point P along the axis. So the axis of this solenoid is here. Okay, is here. So we need to find what should be the H field at the point P along the axis. So let's say we take P is here, and let's say P is having a coordinate of 0, 0, Z. Yeah, Z is a variable. So we need to find what should be the H field produced by this solenoid structure having a length of L with n number of turns and carries a current of I to the point of P, which is having a coordinate of 0, 0, Z. Okay, so the solution for this example will be quite long, yeah. But I will provide the solution for this example 6 in our Telegram channel, yeah. So you can find out on our solutions for this example. So it's very straightforward. We just adopt the answer from example 5 before this example, yeah. So we are using this example, yeah, to solve the problems, example number 6, yeah. So the solutions will be given in the Telegram channel, uh, and you can then understand how we can obtain the H field intensity on this axis of the solenoid, yeah. Okay, so that's the end of lecture 15. So by that, I can see that we have covered successfully the topics of Biot Savart's law, which is the first law that can be used in calculating the magnetic field intensity H. Yeah. So lecture 16, which is the next lecture, will be covering topics of Ampere's second law, ACL, which is also another method that can be used to calculate the magnetic field intensity. So the reference for this topic can be obtained from Sadiko, page of 302 to 309.